for minors, first let's not go to minors. Let's go to something else. So we have K4. So somehow we want to, so K4 is quite dense, so we want to make it sparse. So how, but we want to also preserve some properties, some important properties. A very main way of doing it will be to add a lot of degree 2 vertex. So before the average degree was 3, in fact it was 3 regular, but now it's not, and the average degree comes down very a lot. As many vertices as you put there. But the graph remains planar, and even if I do the reverse process, like I erase all these degree 2 vertices, still the graph remains planar. So this process of adding a few more vertices, degree 2 vertices on a particular edge is called subdivision. And we have seen it in my first lecture, which was Brussels sprouts. And in the game we were doing exactly that. We were creating one edge and subdividing. So this is one very important operation. So in the sense, it's called, it gives me the definition, it gives us the definition of topological minor. So what is it? H is a topological minor of G if there exists a subdivision of H as a subgraph of G, or H in G. So if you want to view H as a, like H is sitting inside G somehow, so what you want to do is you want to subdivide H and then you want to find a subgraph that is inside G. It is a subdivision of H. It doesn't matter how many times you subdivide an H. So if you do 0 subdivision, it is just subgraph. Okay. Okay. So this is what topological minor means. And so the easy way of seeing it is if you forget about all the degree 2 vertices and look at your graph, is this looking like H? Of course, if H has degree 2 vertices, then you should not forget all the degree 2 vertices. You should be seeing. Next one is minor. So H is a minor of G if H can be obtained from G by 2 operations mainly. So the first is actually 2 operations put together. So you can delete any vertex or edge from G, and the next one is edge contraction. So just to recall, what was edge contraction? So you had some edge, let's say UV, and it had a lot of things here. Okay. And if you contract this edge UV, what you, maybe I will name these also, So I will replace this edge UV with a new vertex, we call it just UV, and then whatever the connections were, I will retain them. But then, in many contexts, what we do is we get rid of the multiple edges if they are redundant. For example, in coloring, it's not required. And if I start with a single graph and delete the multiple connections, then I will never create a loop. And there is no multiple edges because I'm deleting it. It remains simple. But it's not always important. But in our context, maybe because we want to simplify things by getting rid of these multiple edges. There will be only one edge. Something like this. So this is simple math. Okay. Now, do you see that if a graph is a topological minor, if H is a topological minor of G, then H is also a minor of G. Because suppose I have this thing inside some G, that will mean that K4 is a topological minor of G, right? Because maybe G is very sparse, large curve or something, but anyways, a subdivision of K4 is sitting inside G. But I'm saying this actually implies that this K4 is a minor of G. How? You delete everything from G other than this part, okay, subdivision. And then you keep contracting the edges. So you will basically, if you contract these two, this edge, so this will be gone and it will be gone. And slow, one by one you can just get rid of all the residual vertices and get a minor. So I think this doesn't require any proof, so I will just write proposition, or it can be observation also. H is a topological minor of G implies H is a minor of G. So I will be using this notation. So here I can say H is less than equal to and sub M for minor. Okay. This is my notation for H is a minor of G. Okay. So if it is a topological minor, it's a minor. But how about the other way around? It's not true. Can you give me an example? Let's see some example. Okay. So, how is this guy? Does it have a K4 minor? Stick to K still. Does it have a K4 minor? So do everyone see that? How? So it is like you contract everything in this connected component, this connected subgraph, and then what you will have is the outside triangle stays as it is, but the inside this red part becomes a vertex, the contract, and it has connection. Okay. So this is one example where it is not a topological minor, but it is still a minor. So H is not a topological minor of G, but H is minor of G. Can you give me infinitely many examples here?
But if we practice some disjoint vertices like the independent set that we can always take to plug it in the for the edges from this, but that can
say it again, please.
so as is set of disjoint vertices.
Independent set.
Independent
Okay.
set. And by contraction in G,
You cannot contract. If there is no edge, you cannot contract.
No, G is some graph.
Yes.
That is set of the vertices
Independent.
of G.
Okay.
Then that is all minor. It's not a topological minor.
No, I mean you can just look at it as a subgraph, right? Don't have to subdivide it.
Independent set you cannot look at by the contraction.
No, but you can delete these. Don't forget the first condition. You can do vertex and edge deletion also.
Sir, can you explain like why it is not topological minor?
So there is no degree to vertex. So there is no subdivision. If it has to be a topological minor, then K4 has to be a subgraph of this. And it's K4 free. There is no, the clique number is 3. Okay? There is no K4.
Take any prism and the related
Yeah. So basically, you can take any cycle of any length, match the length outside, and then you join these. You can also, okay? So this one will have a minor which is K4, but it is not, there is no topological minor.
So where we have a degree greater than 2, it means can we say?
So what is topological minor? You take H, you subdivide it. Subdivide means you add extra. What is the difference between H and subdivision of H? Is that on the edges you have a lot of degree to vertices. So if in your graph there is no degree to vertex, and if H itself doesn't have a degree to vertex, then speaking about topological minor is exactly the subgraph inclusion. So that's what I am using here. Okay? Okay. So this is one way. The converse is not. Right? Fine. And next I will also again define minor equivalent. It's an equivalent definition, which is like H is a minor of G if there exists so I'm actually defining this term also, minor model of H in G. So now I will explain what is minor model. So what is this minor model? That is H1, H2, HK these are disjoint, well they are actually subgraphs. So disjoint means no common vertices or edges. It's not, it's different from what Harminder was saying about touching it. So they may have edge in between them, still they're disjointed. Just disjoint vertex. So disjoint vertices. Disjoint.
Connected, no?
Yes, they should be connected. Subgraph. Yeah, disjoint connected subgraphs of G such that So I also will say something here, something more. So let's say H have vertices H1, H2 up to Hk, okay, k vertices, and then subgraphs of G such that Hi, this subgraph has an edge with the subgraph Hj if, not even only, if Vi incident to Vj, adjacent to Vj.
H is
H. So you see why it works, the equivalence. So if you have this, then what you will do, you will contract each of these HIs, they will become a vertex. And then you have at least one edge, so that will remain. And then you look at it, it is exactly your H. Right? You may have to delete some extra edges, because it's not if and only one. And if you have that, so if you are able to contract things and get H from your G, then you look at, so you see you can only contract vertices and like a set of vertices and make it one vertex if that part induces a connected component. Sorry, connected subgraph. Otherwise you cannot. Right? There is no path, so you cannot really go. So that part will give you the, so that exactly how you got the vertex of H. Let's say H1, you have contracted multiple edges to get H1, and whichever vertices got merged together, those vertices will induce your H, capital H1. Okay? And the statement is equivalent. Okay. So sometimes we need this kind of. Okay. So, fine until now? Good. Now I will recall one exercise question, tutorial question. Maybe some of you did it and not everyone did it. So please tell me the solution for those who have done it. It's easy. So K5 is not planar. Q3 is not planar. So what is your solution? Yes? Yes, but how?
So
There is an easy solution using some of the exercises. So that is one solution. I'll come back to your solution also. So this is because it doesn't, so there was something like E less than equal to 3V minus 6. What is, how many edges does K5 have? 10, right? It's 10. And how many vertices? 5. 5. So it is 15 minus 6. How much is it? 9. 10 less than equal to 9. Doesn't work. So, right? For any planar graph, we have this formula. So it doesn't work. And this is true. Not planarized. How about this one? This works here. It fails, right? Exactly. For triangle free graphs, this formula changes. So just to have an idea, so how much is this? This is 9. Age is 9, and this is 18 minus 6, so this is 12. So this is consistent with the previous general formula, but if you do it for triangle free, then V minus 4, right? Yes. Okay, so age is 9, it should be less than equal to 2 times 6, that is 12 minus 4, but then we get 8. Okay? So again, this is not correct. So this must be planar. But I would also like to show the topological proof. You know? This is, yes, I mean it doesn't get used so much, but technically it does. So Jordan curve theorem is more difficult, not for continuous curves. So here we can assume continuous curves, but yes, using that. So let's look at K5. Okay. Let's look at K5. A, B, C, D, E. Okay. So A, B, C, D, E is a cycle. So in any planar embedding, the cycle should be a closed curve. Simple closed curve. It cannot cross also because of planarity. Okay. So A, B, C, D, E, it should look something like this. It can be something like this also, but then we use topology to make it this thing and that thing, both are simple closed curves, so topologically they are the same. So in your proof, when you actually have to use geometry for planar graphs, you can say without loss of generality, this is a unique topological embedding on the plane of my C file, which is sitting inside my graph. So you can always do this. And you can say speak about vertices which are inside and outside. Okay? And now, let's say I have to put the edge AC. So I can put it from outside or inside. But again, they are the same thing. Because you can draw it on a sphere. So suppose that the 5 cycle goes through the equator. So, it's very symmetric. So inside and outside are basically the same thing. So let's say without loss of generality, I draw it in the inside. But now, B and D, if I want to make them adjacent, I cannot do it from inside. Okay. So why? Because if I do it from inside, just go a little bit. I mean, I know all of you can see it, but I'm just saying how to actually see it through Jordan curve theorem. This cycle is a closed curve, so this is inside. But the part which gets attached to D from this side or that side doesn't matter, that is outside. In fact, the entire D is outside. So once you have gone inside, to go outside you have to cross. You cannot do that, so it must be from outside. But now, how will you draw C and E? It has to be from inside, same logic. But now you are in trouble with
A to D.
E and okay, A to D, it has to be from outside. Now you are in trouble with C and B. You cannot draw it from inside or outside. Okay? Fine. So this is for K5 not being planar, topological. How about K33? What is your answer? So how is K33? How does it look like? It looks like this, right? But for the proof, I don't like this drawing. What I like is, I like this drawing. So let me make a small drawing here. It's exactly this. Okay. You can check the isomorphism later on. But I have a 6 cycle, it will again be a closed curve, and A and B must be adjacent. Let's say it's adjacent from inside. Now C and D must be adjacent. It cannot be from inside, it has to be from outside. But E and F also should be adjacent, it cannot be from inside or outside. It cannot be. So this is geometric proof of K5, K33 not planar. So fine? No. Now it turns out that, so you see, if you think about it very vaguely, you will want to say something like, to describe a class of graphs, if you can say, okay, this class of graphs is exactly those graphs which doesn't have these 5 things as a subgraph, let's say. But that turns out to be very difficult or impossible. Okay? But in many cases, if the case is favorable to me, then I can say, okay, don't forbid the subgraphs, but forbid minors. And then it works very well. In many cases, and we will see in which cases. The first such indication was probably due to this. So also for topological minor it works. So first one maybe is due to Kuratowski. Which says that if you exclude exactly these two things, like K5 and K33 as minors, then it is enough to describe the set of planar graphs. G is planar if and only if K5 and K33 are not topological minor of G. Okay? But then a few years later, Wagner extended it. G is planar if and only K5 and K33, these are not minor of G. These are not minor of G. Okay? So, and in fact, what Wagner said, this is equivalent to, in this case, it is equivalent to the, both theorems are equivalent. So from here you can go there, and from there you can come. Okay. Good. Now I need some definitions. So one definition I like, just a notation maybe. So what I like is for n, so n is for minor and for is for forbidden, of let's say n1, n2, it can be an infinite set also, is equal to, this is the family of graphs which is G such that Ni is not a minor of G for all. Okay? So whatever is inside the bracket, none of these are minors, and whatever graphs are there which does not contain any of these as minors, that family is called for n mi's. And in particular, in this notation, this set is called the Kuratowski set of the family of this class of groups. Right? Okay. So I can make it a little more. I can say this is like this class C, and then Kuratowski set of C. So sometimes what we will have is, we will have this class C and we will want to know if I have a description. Okay? But in graph theory, you not only want structural things, you also want the algorithm parts to work. So usually to do algorithms, it's difficult to handle infinity. So maybe in some cases it will be possible because it's not the input, right? So, but if sometimes it is the input and you are using this information, it may be difficult. So one question you want to ask is that question 1, well, this you can always do. For infinite, if you allow infinite set, you can always do. You take your favorite class of graphs and look at the minimal minors. Okay? So minors which are not contained in another, so minors which you have to forbid. So those graphs which are not in your class and whose minors are not in your class, so you can always do that. So you can give some kind of a description. But the question is, for which C Kuratowski set is finite. Okay. So for C is a class of graphs. So for which C Kuratowski set is finite.
What's the argument for we can always do that?
So you take the minimal minor excluded minors. So it's true, right? Yeah. Because after saying this, I'm starting to think, but I think you can always do that. So, okay. So basically, you take all the graphs which are not in your class. Okay. And now, from these graphs, you see which is minor of each other, and take the minimal ones and delete other things. So it's just take the complement set of graphs. In this, if you have a G1 and G2, and G1 is a minor of G2, then you throw away G2, keep G1, and keep doing this. So you will have an infinite set, but still you can do that. I think that works.
So your C is the whole set in right hand side. Class C.
C is some class of graphs. This C is some class of graphs.
So in that definition, forbidden in this.
Yes, C is this set, equal. Just giving this name to define Kuratowski set of C. So maybe there is a problem, but we'll see. Okay?
Can you please repeat the question? I'm confused.
So, can any class of graphs be defined as forbidden minor?
Minor closed.
Minor? No, not minor closed. Minor closed can be. Okay? But any, even if it is an infinite set of minors. So let's see. I won't vouch for it. Okay? Right now. Okay. So let's see what happens. So it has to be minor closed, I guess, right? Well, of course it works for minor closed, but let's see. Let's keep it pending. Okay? I take back my comment for now. The second one is, so we are somehow this complete graphs are something which were obstacle for coloring, and we have studied coloring also. So another question which may not sound so natural is that okay, sorry. So what if we exclude just a single graph, which is a complete graph as minor? What happens? Do we know what class it is? So question will be, what is the structure of forbidden minor Kn? Actually, it is K. The plus one is fundamental. But I want to say something afterwards where I want n somewhere, so this stays n plus 1. So these are two questions that we have. Okay. So, which one looks easier to you? Second one. Maybe the second one. Second one has something to do. So, let's see. So, tell me what is forbidden, or maybe I should start here. Forbidden K1. Empty, like nothing is there. No vertex, no edge. So not so equal. Let's say this one. Independent space. So this is independent space. So it looks like this. Then for forbidden M, K3. Forest, because it can be disconnected also, right? So no cycles basically, because every cycle you can contract and make it a K3. So no cycles basically. This graph is no cycles. Forest. Okay. Then let's say this is the next example is knowledge based, not really. It's a bit difficult to immediately see it. M. Oh, okay. No, let's continue in this direction. Okay. Fine. So no K4 minor. Yes? Triangles only. So it is a known class of graphs that you have studied this time. It is a superclass of outer planar. It's actually the partial two trees. So I will just write it. I think at some point of time I will prove it, but not right now. Now I just want to give you some kind of a list. Right. So, I will circle to this problem later on. K5. Can you say a subclass of this at least? Planar. Because planar, due to Wagner, doesn't have K5 and K3. But is that all? Or you have other planar graphs inside you? K33 is there. Excellent. So from K33 you cannot get a K5. So K33 is definitely there. And I will tell you, let's see. I will draw one more graph which is not planar. And you can tell me if no, I really wrong. That's good. not a vertex, it's just edges overlap. So this graph is called the Wagner graph. It's not W8V8. So this graph is not planar. You can do the geometric argument. So it's an 8 cycle and antipodals are adjacent. But this doesn't also have a K5 minor. That I leave as exercise. Notice that please. Like, it has K33 as minor. But this has a special, it requires a special mention. So that's why I drew it. And I will draw a small version of it here so that you remember. Just make a small version. And he relieves it at some point. Okay. But then this answer becomes quite difficult. There is an answer, but we will come to it. It becomes difficult. After that, when I do a K6, that answer becomes extremely difficult, and we still maybe have a very complicated answer. From K7 onwards, we don't have an answer. So maybe partial for K6, but it is somewhat understood. For K7 onwards, we do not have an answer. And okay, now let's go to the first one again. It's a bit to and fro. But we will not really discuss the answer of the first question. Rather, we will see some examples. So we saw some examples. Forests. So the other way around. Now the class is given, and I'm trying to identify. So this was what? A forbidden something is given, minor, and I'm trying to guess the class or characterize the class. Now a class is given, and I'm trying to get a forbidden minor characterization. So here I have 3 examples. If independent set, forest, or partial K tree is given, I know forbidden something, and I want it finite. Okay? So the third example you have here also. So at this point of time, I would like to change this state. Change means not change the meaning, but I would like to say forbidden M K5 and K33 is equal to this. This is the exact same state. Now, how about what classes can you say? So, let's see. Do you know what is a projective planar graph? Or projective? So, projective. Did you play Pac-Man when you were kids?
Yes,
Yeah?
yes.
It's a weird Pac-Man. So, torus is Pac-Man, and projective planar graph is not Pac-Man, it's a bit weird Pac-Man. So torus, let's see. So this is for torus, and this is your computer screen if you play Pac-Man on projective planar graph. So I will say projective planar. Okay, this is torus. Torus is this tube, right? But what happens is, in Pac-Man, what used to happen? This guy goes here and then enters from this, right? So it is like this is folded, and the left side edge is identified with the right side edge. So you make a cylinder. And then if you go out from the top, you come out from the bottom. So it is like the top edge is identified with the bottom one, that also makes a cylinder. But now take this cylinder and identify the left and right, you'll get a torus. Okay? So this is normal time. Projective plane, Passman. If you go out from here, you actually come out from this side. So this gap and that gap, mostly same. I mean, it's topological, so the distance doesn't matter really. And if you go out from there, you enter from here. Okay? So it's folded, but with some twist in the back. So these are orientable surfaces, and these things correspond to non-orientable surfaces. These are the simplest examples. The sphere is also orientable. So, but I will not go too much into that. And the torus actually looks like how you are familiar with. So it is like this kind of thing, and then there's the other way around. There is a hole inside it, right? And two torus is easier to visualize than the genus 2 here. So genus 2 torus, it will be like so there is a hole here and there is a hole here. Okay? So two holes. Kind of, yes. There is some transformation where we can go. It's not exactly, but it has some flavor. Okay. So the graphs, if you draw on Mobius band and here, they may coincide. I'm not entirely sure, but I think I saw it somewhere. They will coincide. So, but again, that's not a confirmed statement. Okay. I have to check. And then 3 torus will be more. So there will be 3 holes, and so those holes, number of holes is called genus. Okay. At some point of time, I will spiral back to this. For now, I will use one of them. So let's say projective planar graphs. So what are these graphs? You can draw it on this without crossing. Okay? So you'll see you can actually draw K5 because of this. You can draw without crossing K5. Here you can do a bit more than K5. So, anyways. Now the question is there a forbidden minor characterization of this with finite set of minors? And there is one. It's something from 1981. Arcadian, someone with Arcadian. So how many things are here? For planar there are 2. It's not the usual one that we saw there. How many? Any guess? Any number. It's not a mathematical guess, just a guess.
28.
Hmm?
I was just telling one.
Yeah, what is your number?
28.
28. It's close. It's 35. 35. By the way, projective planar graph also has a induced subgraph, forbidden induced subgraph characterization that has more than 100 graphs, some 130 graphs, 120. So, but we like forbidden minors more, and that's the topic. Let's say for toroidal graphs. So these can be drawn on the torus without crossing.
So one torus or 2 torus?
One torus. It is a very big number. So, okay, you are saying 1100. 17,000 plus, and it's complete. The list is not complete. It is known that it is finite. Till now they have found 17,000, and somewhere in the world, in multiple places, there are some coding running which are finding new forbidden configurations. Probably that is also true because, like, I was working with Diban and telling this to Flo, and it was a lot less at that time, some 10 years back. And anyways, we will know. That's what the point is. After it's coming soon. Okay. So it can be very huge, and really, if I am planning to use these information for my algorithm, it may become very impractical.
Toroidal planar graph only.
No, it's called toroidal graph. It means that you can draw it on the torus without crossing.
Edge crossing.
Because without the edges crossing. Yes. So this is called a projective plane. That's why it's projective planar graph. It's not planar. Okay.
Are projective planar and toroidal graphs comparable? Like, can you draw every projective planar graph on a torus?
The other way around is not true.
Yes.
Probably. Again, not sure.
Yeah.
I think it is true.
I'm not sure.
Yeah. So the genus 2 orientable surfaces will be claim bottle. That's the second example people give. And it's like you take a bottle, you take its the pointy side, and you put it inside the back side, and then it becomes a project. It somehow looks like that, claim bottle. You can look at it. Maybe Meghna knows better than me. She's an algebraist. So. Okay. Now I again need some kind of. No, I have one more. So. Linkless graphs. So what is linkless graphs? These are actually quite interesting. So you know you can embed every graph on 3 dimensions. So you can just put some vertices as a coordinate of the 3D space and put edges, and you can, or curves, okay, continuous curve to join them for edges, and there will be no crossing, and you can do that for every graph of linkless and do that. Okay, so you can embed all graphs in 3 dimensions, which you cannot do on 2 dimensions, and you get only planar graphs. But then, if you forbid one particular kind of a structure, so cycle will also be a closed curve in 3 dimensions, right? So this is a cycle, let's say, this whatever I did here, and then there is another cycle. If they are like this, then we say they are linked. Now I'm saying there exists an embedding which avoids this kind of a link. Okay? Then it is called linkless curves. And they are quite important for some reason. So it was extremely challenging and a celebrated result. The forbidden minor characterization of this 7 Peterson. It's not visible, but doesn't matter. It's 7 graphs, and they are all from the Peterson family. So there is a family of graphs, including the Peterson graph, which is called the Peterson family of graphs. So there are 7 special graphs from this family, which if you forbid, you get exactly the linkless graphs.
Was it 7 exactly?
Exactly 7. 7 graphs. Yes. Okay. Peterson graph. Okay. Next. Okay. So I'm going to define something called a k-click sum. So you take a graph G, let's say G1, and this plus O plus with a subscript k means I'm doing a k-click sum with G2. Let's say this is equal to G. So what is it? I will just define it using pictures. The formal definition you can construct also. So you take your G1, you take your G2, you identify you find a k-click here, you find a k-click there. So these are all k-clicks. This is KK. Okay. There are subgraphs which are complete graphs. Okay. Now what you do is, you have k vertices here, k vertices there. Let's say 4. You identify them. You glue them to each other. In any order. The order doesn't matter. Okay. So that way it's not very well defined. So if I do it with G1 and G2 and you do it, we may get different graphs. That's fine. But the process is called k-click sum. So what we will do is, maybe I should have used more colors here. So this yellow part and this red part, they coincided. And so one vertex glued to one vertex. So it's a bijective glue. Okay. But the definition doesn't end here. After that, you are allowed to, from this portion, allowed to delete some edges. So you are gluing with the k-click, but you can delete some edges of the k-click. So in some cases they use this definition, that delete some edges. It's more general. In some cases they don't. So yeah, k-click sum is done. Now you see why I listed this and then defined that. So I will erase it soon. But they have a relation. Why this operation is important. So this operation is very important because it kind of helps me describe these kind of things. Let's see, forbidden K2 minor, this class is just independent sums. So I can say that it is zero click sum of K1s. Right? Trivially true. You take a K1, no click identifier, you take another K1, you keep taking K1s. So this guy is exactly zero click sum of K1s. So this is exactly and there is no negative, but I will still say like this. Click sum of K1s. Now, how do you create a tree? Remember the one tree definition? You start with a K2 and then keep identifying one vertex. Okay, taking a new vertex, add it with one. So I can also say similar things here. That is, it is less than equal to 1 click sum of K1s. Right? So how about the next one? Forbidden K4? K2s. Yeah, sorry. You're right. K2s. So how about this? Can I make a similar comment? So what will be the things that forbidden minor K4 equals to graphs obtained by doing a bit of abuse of notation less than equal to 2 click sum of K3s. Maybe? Yeah? Let's try to prove it. So how do we prove it? So what was our favorite statement of the first line of the proof again? Minimal counter example. Let G be a minimal counter example. So what does it mean? That G is a so by the way, with 2 click sum of K3s, you cannot create a K4 minor. You see that easily. So because for K4 minor, you kind of need, I don't know, is it easy to see? Okay. So but the challenging part is the other way around. So that's what we're proving. That suppose G is a forbidden K4 graph, forbidden K4 minor. So G doesn't have a K4 minor. And I want to show that I can obtain G through this less than equal to 2 click sums, okay, of K3s. So first case, if G is disconnected, you have a component C1, another component C2, delete C1, C2 remains. It is also forbidden K4, like it is not also K4 minor free. So you can construct this using our rule. Delete this, you can construct this using our rule. Okay? And then merge them together. So it's an okay process. Now, so G cannot be disconnected. G has a cut vertex. Okay? G has a cut vertex. So
what are you trying to prove here? Prove this is false.
I'm trying to prove this.
So counter example should be.
So minimal counter example, it cannot be disconnected. This is what we do.
No, but you're just proving one side of the equality. Which side are you proving?
Okay, so I should say that. So I'm showing that all forbidden K4 can be constructed like this. So if G has a cut vertex, then it looks like this. The disconnected case. So you have at least 2 components. You take one component, you delete it. So what you have is smaller than your minimal counter example. It is also K4 minor free. So you can construct it using my process. Click sums of K3. Then you delete that part. What you are left with is with the first component, and that is also smaller than G. So you can construct it with that process. So you do this separately and you will be able to do it. Okay?
But technically you should be allowed to remove vertices also.
Hmm?
You should also be allowed to remove vertices, not just edges. Because if you take the triangle, I mean a graph on one vertex is also okay for my theorem. But
Delete some here, you mean? Yes, yes, yes. Slash. Okay. Yeah, so if you have a cut vertex, then again something similar. So you take this part, it is smaller, and you take this part, this is also smaller. So each of them you can construct and then do a one-click sum. Okay? Then you go to, if it has a two cut,
Then this G should not have a cut vertex.
yes, so G doesn't have a cut vertex. So it is at least two connected. Now suppose it has a two cut. So what you do is, well, this is a little bit tricky because this, whatever this cut is, it may or may not be connected, right?
I'm sorry, I missed that part. What happens if it has a cut vertex?
So if it has a cut vertex, so it's like this, right?
Yeah.
So you take this part and that part
Right.
separately. Both are smaller than G and doesn't have a minor. So you construct them with click sums, and then you join with a one vertex. One click sum.
Oh, okay.
The parts including the cut.
Yes. So when you do this, you are actually including the cut vertex in both sides. Okay. So the next one, okay, if it has one edge, then it is easy. You do the exact same thing. So I don't know how to draw it actually. Some y. Okay. So this is C1, C2. Okay. So if x and y are adjacent, then it's easy. You just separate them and you construct, right, this yellow part, you construct the red part and then do a two-click sum, which is allowed because less than equal to two-click sum, and you can construct. But the problem will be if this is right, but then you know it is two connected. So the connection is also inside this C.
Because we assume that C1 and C2 are not monoconnect. I mean, connectivity is at least two, right? That
Yes,
we
yes, yes. The whole graph has connectivity too, and C1, C2 also should be two connected.
Correct.
So then it has a path inside C1. So when you consider this red thing, it actually has a path through C2. So there is a path through C2 between x and y. So when you take out this red thing, also take this yellow path along with it. Maybe it should have been red, but it's easier to understand. Okay? So not only take this xy vertex in your red set, but also take this red path which is connecting x and y through C2. Now you contract that red path and get an edge here. Okay? So you have now your C1 with an additional edge. but you have only contracted edges and deleted some extra vertices and edges of C. So you are still in your forbidden minor closed class, K4 minor free graph. You do the similar thing with C1 because there is again a path, so that path along with it. So you create C1 with XY edge. You create C2 with XY edge. Glue them by 2 clicks up. And now you delete the edge and you get your graph. Okay?
Why are the two paths and two different C1 and C2? I can't get it.
So it should come from C. Maybe Sandeep can help me out here. No?
Oh, but each is a connected component, no?
Sorry?
You have 2 components, right?
Yeah.
So it's
Right.
connected, so there is
It is 2 connected components. So yes, thanks.
I mean,
So
actually,
if you
could have multiple components.
If you have multiple components, then you do it multiple times. Okay. Thanks. Actually, you can say C1 is one component and C2 is the... No, you have to do multiple components.
So after contracting that red path, we are getting an edge.
Yes.
After that, what will we do?
So we are getting an edge, but this whole graph, like C1 with XY edge, this is a forbidden K4 minor, so this is a K4 minor free graph because I have done only contraction, right? And this is smaller than G, so I can construct it through my operations. And similarly, I get C2 with the additional edge, and I glue them. Yeah, I do 2 clicks up and delete the edge. Okay, so G cannot have a 2 cut. Now that is enough. That part is enough. So G cannot have a 2 cut.
One corner case, like what if the red path is the entirety of C2?
No, still it is not a corner case because you will contract it, get one edge. Still your graph's cardinality or the number of vertices is equal to the vertices of C1, which is strictly less than G. The minimality condition may be number of vertices. So G is 3 connected. If G is 3 connected, definitely G has a cycle. Okay? But that's not the only thing G has. So, for example, this. So G will have at least one more vertex. It's not just a cycle. Now this vertex, maybe you take the smallest cycle or something. Then you will have at least one more vertex. Because there is no chord, so X and Y must have one more internally disjoint path through them, and there has to be another vertex. So just I need existence of a third, a vertex which is not on the cycle. Now this V, because of 3 connectedness, it will have 3 distinct internally disjoint paths with say X. So what it means is it will have 3 different paths, internally disjoint path with the cycle. Okay? That is a K4 minor. So G is 3 connected, then you have a K4 minor.
So, what is V? How did we get V?
So you take the smallest possible cycle, so you know there is a cycle in G.
Because of 2
Yes. You take the smallest possible cycle in G. So 2 vertices in this cycle, through the cycle, has 2 paths, 2 distinct paths, but not 3. So for the third path, and it cannot be a chord, direct edge, right? It cannot be a chord because you have taken the smallest cycle. So there is some other vertex, definitely, in the third internally disjoint path. You take one, so you know, apart from the cycle, you have another vertex. Now you forget about the internally disjoint thing. I drew a cycle and an isolated vertex. But this vertex should join the cycle in 3 different ways. So I get 3. So these are all paths. These are paths. Okay? And I have a K4 minor now. So 3 connected implies K4 minor. Yeah? Yes, it is done. Yes. Yeah. So this side is done. Forbidden K4 is inside. So all forbidden K4 graphs can be constructed through less than equal to 2 click sum of K3s, begin with K3. Okay. And what are the less than equal to 2 click sums of K3? They are exactly 2 trees, and then you are allowed to delete some edges or vertices. You can just glue them anywhere where you want to delete and delete the whole thing. So it is always possible. So these are exactly partial K trees, even though I did not show the other way implication that you can do.
2 trees,
That part.
not K.
Mm-hmm.
2 trees.
Partial K, 2 trees.
2 trees.
Not K, yeah. Partial 2 trees. So I will just put the equality here, and the other way, I have shown the more difficult side. One side can be exercised. You see that if you do this process, you never create a K4 minor. Okay. So these are exactly partial K trees. Sorry, partial 2 trees. And then we have 2 trees. And the same trend continues here, right? So this is equal to less than equal to 2 click sum of K trees. How about next? Does it work anymore? So I'll tell you the answer that it doesn't. Okay? It fails. It starts failing from K5. And that's one reason why planar graphs are kind of so important, because many problems in practice you will see it becomes so you have what do? You get a problem, you look at a sub-problem and continue to increase the difficulty, and once you reach planar graph, many times it happens, it becomes very, very difficult. And so you think that if you can solve it for planar graphs, you have developed a lot of techniques and maybe you can extend those. And many times that happens. So planar graphs are regarded very important. So I will tell you the answer for this without proof. But the answer is already quite nice. I like this answer very much. So it is less than equal to 3 click sum of So in your box, you take all planar graphs, and you also take that V8. Now you do all kinds of click sums and fill your box with that. The family you get is exactly forbidden K5 minor. Okay? Now notice something. Oh, I'm going very slow. So notice something that what is this V8? How many colors do you need to color? 3 colors. Okay? This is a triangle free graph and you need 3 colors. You will see. You can observe that. Okay? Now, if you take a 3 colorable graph and another 3 colorable graph, you do a 3 click sum. So the whole thing is 3 colors again, because those 3 colors and these 3 colors you can coincide. It's a click, so it has got 1, 2, 3. This has got 1, 2, 3. and you permute this 1, 2, 3 to match the color, rename, and glue it. So planar graphs are 4 colorable. V8 is 3 colorable. So K5 minor free graphs are 4 colorable. And that is actually equivalent to the 4 color theorem. So if you prove the 4 color theorem, along with, this is due to Wagner, this will, due to Wagner, this will be 4 colorable also. So actually this forbidden K5 minor, colorability of it is considered to be 4 color theorem also. Okay. Now, how many colors do you need here? 1. 2. Partial K trees. It's 2 degenerate because there is a degree 2 vertex always, the last word. 3. 4. So, chromatic number of forbidden minor K n plus 1. That's why I had written K n plus 1. How much is this? Okay. Why? No, I don't know. Years. Okay. It's considered one of the deepest conjecture in graph theory. It is also proved for n equals to, so K6 minor free, so n equals to 5. This is n equals to 4 in my language. So
7 is also
no, 7 has partial results. So what they prove is that for 6, what they prove is that they again take a minimal counter example, okay, and then they try that the minimal counter example cannot be disconnected, cannot be 1 connected, 2 connected, etc. And then finally they say the minimal thing should be some 5 or 6 connected, and then they say this minimal counter example has to be of this form, the following form. What I am going to say, that it is planar graphs plus 1 vertex, and that vertex has a lot of connections. So you delete that vertex using 4 color theorem, you color the graph with 4 colors, put this back, color this one with a 5th color. So the minimal counter example is 5 colorable and a contradiction, right? So for n equals to 5, this is known to be true for K6 minor graphs. And that is also considered to be equivalent to the 4 color theorem, because the first part of the proof says it is just planar graph plus 1 vertex. That's how the proof. So there are 3 characterizations of planar graphs. And then for the n equals to 6, what is known is if there exists a critical graph, how many? 6, right? If there exists a 7 critical graph, then it must contain a K7 minor. If I stop here, then it is proved. Or a K44 minor, or a K7 minor, or both a K44 and a K35 minor. Okay? So if you remove those 2 conditions, then you can prove. So it's not proved here. And for 8 onwards, it's wide open. Okay? So this is the Hadwiger's conjecture. And in the proof of this K equals to 5, that linkless graph is used somewhere. Okay, so I will skip a few things, I guess. And I will directly go to the easy statement of graph minor. So I will go with the easy statement of graph minor theorem, which is so what is a minor closed graph class? So a class of graph C is minor closed if G in C, H minor of G implies H is also in C. You take anything here, take a minor that is also in the class. C is minor closed implies C equals to for M for some finite set of terms. It has a equivalent formulation which is more classical. I'm not going to the well quasi ordering, but what I will say is that N1 to 2 implies there exists time J such that in time. So this is an equivalent formulation. This theorem is by Robertson and Seymour. It's the famous Robertson and Seymour theorem. It's like 20 papers and 500 pages long, and it took around 25 years to solve it. So 1986 to 2004, and more than 28 years. And it's one of the deepest theorem in graph theory. So you see, what I'm saying here, if you take infinitely many graphs, then there will be two graphs in this infinite sequence. One of them is a minor closure, the other. Okay? So, if you have a minor closed graph class, and you have a forbidden minor characterization, from here you can imply that it should be finite. Okay? Try that. I'm skipping that part, the details. It's not extremely difficult. Anyways, because of this, yeah.
So this statement says that if we take any infinite
Sequence.
then
Yes.
there are two points minor of other.
Yes.
So it is any sequence of graphs or
Any
in
sequence.
the minor closed.
No, any sequence.
So
No, they are equivalent, actually. Okay, so, by the way, the same thing does not happen for subgraphs or induced subgraphs. You take all odd cycles, that's an infinite sequence. None of them is all cycles. They are not induced subgraphs to each other inside.
I think subdivision also doesn't.
Subdivision also doesn't.
You have infinite sequence.
Okay. But now I want to do something with it, and maybe I will just add one more theorem, which is after this. Also, Robertson Seymour. So, if you give me two graphs, H and G, and you ask if H is a minor of G, this problem can be solved in polynomial. In cubic polynomial. Okay? So it's a cubic time algorithm. Now, remember I told you about linkless graphs. There is another kind of graphs which is called knotless graphs. So knot is like you tie a rope, right? So I cannot do it with my hand, but something like this. Yeah, actually it is correct. No, I cannot do this. It is a simple cycle. So basically, any cycle, if it is a simple cycle in your embedding in 3D, so you have a graph, you are embedding it in 3 dimension, and every cycle is a simple cycle. Then it is a knotless graph. But if it is a knot, like you cannot actually untangle it and make it a simple cycle, then it has a knot, basically. It's not your knotless graph. So it was not known that whether given a graph, if you ask this question, you give me a graph and is it a knotless graph? The answer of this question, whether it had an algorithm or not. So it was not even known that if this is solvable algorithmically or not. Forget about polynomial or anything.
Decidable.
Yeah, decidable or not. Even if you have a super exponential thing, then people will be happy. But with this theorem, you see knotless graphs, if you contract, still the knot remains. So it is a minor closed class of graphs. So with these two theorems, we have a cubic time algorithm to solve that problem. There exists a cubic time algorithm. So something which was so difficult that we didn't even know if it is decidable or not, at one go it becomes like there is a cubic time algorithm. Okay? So it's very strong, this theorem. These two theorems together. Okay. And tree decomposition is okay. Tree with two, no? Tree decomposition. Okay. So I'm not writing the every details. So I'm just writing two conditions. Actually, this was my Q2, but I forgot the host comment. Okay. So, I'm saying, Flohon gave some definition of tree. What was it? Every vertex should be part of some bag, every edge should be part of some bag, and if you take the induced graph of bags which contains a particular vertex, it should be a connected sum. Right? These were the three conditions. Now what kind of conditions I am giving is if V is a vertex, then the subtree which is induced by the bags which contains V is non-empty. So that means it is inside some bag. And it is also a subtree. So it is non-empty and it is connected. When I said T, it is actually a tree. So it is a subtree. Tree is always connected, so I don't have to say connected subtree. And the second one is if you have an edge, then the vertices of U and the subtree of U and the subtree of V, the intersection is non-empty. That means there is at least one bag where U, V both are there. So you take TU, which is the subtree induced by the bags which has the vertex U. And then you also take the subtree which is induced by the bags which has the vertex V. And I am saying these two subtrees, they should intersect somewhere. So they should have a common vertex.
So that common vertex could be similar, but not necessarily U and V.
But that vertex is a bag.
Which contains U and V.
That bag contains U and V. So if these two trees have a common vertex, so all these trees are what? They are made of bags. So that means they have a common bag. The first bag, and that bag is inside TU means it contains U. It is inside TV means it contains V. So both are. So this is the, these are the conditions you have. And, okay, quickly. So this is an alternative definition of tree decomposition. Okay? It's the, I just explained that why it is alternative, why it is equivalent. So I did only one side, so you can do the other side. G. Okay. So what I'm saying is that suppose H is a minor of G and G has a tree decomposition. I'm saying there is a way that I can make this decomposition also work for H, the minor. So how I will do it is, so how is H sitting inside G? So there was an exercise where you proved that if H is a subgraph of G, then the same tree decomposition works. Okay? So it is something similar, a bit more important. So take a minor model of H. Remember there was an alternative definition somewhere that there is this minor model. So what is it? Some connected subgraphs of H, disjoint. Each subgraph corresponds to a vertex of H. Okay? So what does these subgraphs have? They are connected subgraphs. They have many vertices of G. Now these vertices are part of several bags. So whenever a bag has at least one vertex from HI, capital HI, in my tree decomposition of H, I will keep this bag corresponding to the small HI, the ith vertex of the sub. And then I will have a, so I think I should work a bit more. So you have a tree decomposition. Okay. Now, your H1, suppose, is made up of A, B, C, and D. Okay. So H1 is the minor model corresponding to the vertex, small h1. Okay. H has these vertices, H1, H2, Hk, and after contracting the capital H1, it becomes the vertex small h1, Hg. So H1 has A, B, C, D, E. So suppose this is A, this has A. All these have A. these two have D, maybe this one also, and say C here and D somewhere. Okay? So I will erase all these things, all this A, B, C, D. Wherever there is A, I will put H1. Wherever there is B, I will put H1. Wherever there was C, I will put H1. Wherever there was D, I will put H1. Okay? Now I have a tree decomposition, which was a tree decomposition of G, but there will be only vertices which belong to H inside the bands. And that will become, you can see from here, because for every vertex, the tree will be non-empty. For A, B, C, D, each of them it was non-empty. It will be non-empty for this also. Will it be connected? A, B, C, D is a connected subgraph. So their tree actually intersected somewhere. So as a whole, the union is also connected. The first condition is okay. The second condition is there is an edge. So that means there is an edge between like H1 and H2 somewhere. This may be A, this may be, let's say, Z. Okay? But there is, so you know now the subtree of H1 is a connected subtree. H2 is also a connected subtree. And you know, somewhere in my graph, A had a tree and Z had a tree. Those two trees intersected. But now I have something bigger than the tree of A as H1's tree and bigger than the tree of Z as H2's tree. So they will also have a bag where there is both. So wherever this bag was, which had A and B, it will be H1 and H2 now. A and Z, it will be H1 and H2, and those two trees will also intersect. So that will satisfy condition 2. So I can say that this tree decomposition of G is also a tree decomposition of H. So that's the thing. That's the proposition. So the tree decomposition of G is also tree decomposition of its minor. From here what I can say, and the size of the bags did not increase, it decreased. So from here what I can say is, H is a minor of G implies tree width of H is less than equal to tree width of G. Okay. Next thing. This I will not, maybe not write. I will write the thing that implies, the thing that is implied for you. Now take two graphs. G1, G2. Do a click sum. Okay? Take a tree decomposition of G1. Take a tree decomposition of G2. So these are two disjoint trees. They have no connection. But if I can put one edge in between them, then they will become one tree. But you know, the click where we have identified them, that click completely contains in some bag. At least one bag. Pick some bag which contains that click in G1's decomposition. Pick one bag which contains this click in G2's decomposition. Add one edge. Okay? So you add one edge, and now together this becomes a tree decomposition of G1 plus G2. So I can write the next implication: G1 and G equals to G1 plus G2 implies tree width of G is less than equal to max of max of tree width of G1, comma tree width of G2. Okay. So this one I can see.
Why isn't it tree width of G1 plus tree width of G2 minus K?
Sorry?
And we are attaching the tree decompositions with
Yes.
the K click which.
I'm not merging them. I'm just putting an edge between them. So the back size stays exactly the same.
Fine.
Okay. But whichever has the bigger back size, that will be your tree. And we'll have a minus one everywhere. Okay. But now the first theorem has a special interest. Along with, I have erased it. So along with the graph minor theorem. So you see, if you have a minor closed class of graphs, if you have a bounded tree width class of graphs. So take all graphs whose tree width is bounded by K. So let's say, let C equals to G such that tree width of G is less than or equal to K. Okay? Take this class of graphs. Take any graph from here, take its minor. Because of the first theorem, the top theorem, that graph is also in the same class because it has low tree width, right? Now using the graph minor theorem, what we can say is finitely many minors. If you forgive them, then you can exactly describe this class. Because this class of graphs is minor graphs. Okay? So that also means that you can recognize this class of graphs in cubic time. Well, cubic times whatever this finite number is. Sometimes this number is very, very big, as you could see. So, but there is an algorithm if you take this finite number as a constant or something. So, I think that is something I also wanted to say.
So finite means some finite graph, not set all finite graphs.
No, of course. So no, finite means there are finitely many elements here. So the set is finite. Finite set. Yes. Okay. Okay. Maybe figure out. So tree width of G less than or equal to 1, G is a forest. I think this was one exercise, right? And it is if and only. Okay. Similar things. Tree width of G less than or equal to 2, if and only if G is a partial 2 tree. So what's the proof? So partial 2 tree also means, now I know that forbidden M K4. So I will somehow use that. So what is the tree width of a complete graph? Kn, n minus 1. So what is the tree width of K4? It is 3. So of course K4 is not here. And if something have K4 as a minor, that thing's tree width will be at least bigger than 3 or more, because of this one. So definitely it is K4 minor. So tree width, tree width less than or equal to 2 must be K4 minor. And then I also have this one. This is equal to less than or equal to 2 split sum of K3s. Right? I also have that. This I have proved. So K3 is 3 with 2. If you take split sum of 2 K3s, because of this, it remains 2. If you do it multiple times, it remains 2. You take subgraph, it remains 2. So 2 trees have 3 with 2, and partial 2 trees also have 3 with less than 1. So the other way. Okay? I'm actually using all these 3 examples. Okay. Yeah, I think I will just say one last thing and stop. But that is a bit different topic, but I wanted to state that anyways. So, until here, are you okay? I think I can wrap up in 7 minutes. So, any questions until now? Okay? Done. Yeah, so, graph minor theorem is here. I should also add this set so that finds. So, usually this graph minor theorem is stated in the language of well-Cauchy ordered set, which is essentially that. And, yeah. It is. So what we did is we kind of said that these minors are, because one big reason is the Robertson-Seymour theorem and the algorithm associated to it, that you can calculate these things easily. And then it has a relation with tree width, and then forbidden minor and tree width, they have a relation, and they, both of them have some relation with the click sums. This operation click sums, but it doesn't work after you go up. Like it works for small forbidden k minor sets, not for everything. So one way, the way they have proved this, it's 500-page proof. So I don't know the proof, but I know some basic idea I can give you. So what they're saying is, suppose you have a minor closed class of graphs, and let's say you have suppose you have a minor closed class of graphs, and you have a forbidden character. So you will have a forbidden characterization of it. That may be infinite, okay? But sort your infinite sequence in decreasing order or in increasing order of number of vertices or something. So you just sort it in. No, you don't have to sort. You just do it like, just write them, M1, M2, M dot dot, something like that. You take M1 and you also say that suppose we have taken a set of forbidden minors where I cannot drop any. Like this set has the property that Mi is not a minor of Mj, because then I will drop Mj. I will keep only Mi. Minimal one, but it may be infinite. Okay, one minimal. Now, so in particular, M1 is not a minor of anything else. but M1, as many, so what I can say is that G doesn't have a, so K M1 is not a minor of G if I take my graph from here, from this case. The complete graph on M1 vertices, G doesn't have this minor because it doesn't have M1 as a minor, but now I'm adding some edges and making a bigger thing. This also is not a minor. Now there is some other theorem which says that if you do not have a particular complete graph as a minor in your graph, so if your graph is Kn minor phi, then your graph is embeddable on a surface, orientable surface of genus Fn, some function of. So you know, now your graph is embeddable on a big surface. Okay? And
What is mod M1?
Hmm?
What is mod M1? The number of vertices?
number of vertices in M1. So now you embed it there, and then, so it's not exactly embeddable there, but it can be almost embedded there. Some vertices will be here and there, but that is also some finite number of vertices. That will join to your, so there is this surface where your graph is laid, but there are a few vertices hanging above in the sky, but from that you are connecting one part of the graph. These vertices are called apex vertices, and the part that you are connecting to has bounded tree. Okay? So somehow, and then there is a long story, so a big proof, but this is the idea how they kind of lay the basic foundation, and then they see that these things can always be described as some forbidden minors. A finite set of forbidden minors. So it's more or less this. It's a bit vague because I don't know the proof, you know. Everywhere I see these ideas, and from there I have made my own idea to give you some kind of a vague idea. Okay. Okay, now the last thing. I will erase all of this and we will go to the next. So I will just state some theorem and say that it's good. That's all. And usually to state this theorem, I need to explain two definitions. One of them you know, the more difficult one. So I will have to just explain one definition. G is planar implies there exists H Flohar, Harminder, can one of you please check if I'm writing correct statement or not? Especially this planar. Yeah, it has to be.
H is planar necessarily.
Yeah, that's what my logic is.
So this time H can be planar.
This time H is
Yeah.
planar.
Yeah.
Okay, so this symbol is for strong product of graphs. So if you take two edges and do a strong product, what you get is this. So in particular, this, so in general, strong product, you take two graphs. The strong product of it has the product of their vertex set as vertex set. And if UV and XY are edges in respectively G1 and G2, then the rule of the adjacency is this, and that's all the rules, there are nothing extra. And in fact, this I like it because I like this notion in the sense that the symbol comes from that picture. So for Cartesian product, you have this, and for tensor or categorical product, you have that symbol. So it's basically the symbol defines the product. But anyways, our thing is strong products. What we have is, if G is a planar graph, the theorem says that there exists a H with low tree width, and here low means less than or equal to 8, and there is a path. You take H and the path, you take its strong product, your planar graph is sitting inside it. Okay? But many times what happens is, so many algorithms are, many NP-hard problems are polynomial time solvable for bounded tree. And sometimes those algorithms can be translated to tree width time, so H times path. So strong product with path is again a bit better understood than other things. So that algorithm translates and you get very nice results. Same thing here. Here in fact you have H to be planar and tree width at most 3, which is very good. But then you have to do one extra strong product with K3. So it's like a cube kind of thing. Many edges inside. But then G sits inside it, and the same thing. That several algorithms are work nicely for tree width less than or equal to 3, and that also
G will be a minor or a subgraph?
subgraph. It's just sitting inside. And these two theorems, there are multiple authors. Duzmovic, I may not be even pronouncing them correctly. Jore, Misek, Morin, Vicare, and David Wood. Okay, and this is a Fox paper 2019, and immediately after this paper came, so there is some survey where I read within some 10 months or something, people solved conjectures or open problems in Q numbers, non-repetitive coloring, P-centered coloring, L-vertex ranking, adjacency leveling. So at least one conjecture or open problem which is at least like 25-year-old and could not be solved. They solved it using this. Okay? So you can think of it like a factorization of G. So there is prime factorization. So it is kind of a factorization of G, and not exactly because G sits inside it, but it's very close to that. And then now the next things that people are trying, they are trying similar factorization because planar graph is a very difficult thing. They have done for that. Now they are trying for graphs on surfaces, especially orientable surfaces, and then something called apex minor free graphs. So maybe you have to remove some apex and then minor. And two things that we know, so minor free graphs and topological minor free graphs. So they are tried. So there are now many other. So this is called product structure theorem, a graph planar for planar graphs. So
it has been 2 to 6 recently. It has been 2 to 6 in this.
is it so? Okay. I don't.
The same route.
Okay, maybe.
I think 6 for something called simple tree width, if I remember correctly, right?
No, so they have, I think, maybe the extra factor with this K3 thing or something like that, but the 8 was improved.
Okay.
It's some
So this is what I got in the survey. So maybe it has been improved because people are trying very hard to do these things. And so there are many other product structure formulations now, theorems, for these other types of graphs, surfaces and everything. So I'm nowhere near expert of this. I read it recently, to present here, and so I'm just going to state this. That's all. You should know that something like this is happening, and you can look at it. Okay. Thank you. That's all.